Hello everyone. In this session, we will understand the different kinds of stacks. In the previous session, we understood why the stack is needed in a computer system because the programmer has to provide a convention to store the previous program counter's values when a routine calls another routine. In order to accommodate the nested subroutine calls, in addition to the recursive functions, we use stacks. In addition to which, stack has many applications. The applications of the stack are as follows. Stack will store return addresses, of course. In addition to the return addresses, stack is also going to hold the local variables of a function. In addition to which, when a program is suspended from the CPU and another program is coming inside, the current program's flag register will also be pushed into the stack. Flag register can also be called as status bits, can also be called as program status word. So the stack is essentially going to hold these three elements. Now let us understand what are the different kinds of stacks available within a computer system. There are two kinds of stacks. To make it very simple, there are two stacks. One is register stack and the second one is memory stack. Again, what is the difference? Simple. In CPU, we do have a stack. That stack is called register stack. In memory, we do have multiple stacks. All those are called memory stacks. Why we do require a register stack? Why do we require a memory stack? You know that every program requires a stack. Every program requires a stack. Let us understand the relationship between the CPU and the main memory. The CPU always is going to execute one program all the time. Let us go to the main memory. In the main memory, we do have multiple programs loaded. This is program 1, this is program 2, this is program 3, and this is program n. Now CPU is executing one program, let us say P2, and CPU holds a stack. Now the inside stack of the CPU is exclusively used for program 2. That is, as long as one program is getting executed within the CPU, that program is going to exploit the register stack. And when a program is available in the main memory, it will be provided with its exclusive stack. So every time when a program is executing within the CPU, the current program that is being executed within the CPU is going to use the register stack. The moment it goes out, this stack will be used by another program which is going to get executed next. This is what the usage of the register stack. Now, let us say initially P1 is getting executed. Now, this stack is exclusively given for P1. Now, P1 is going to hold local variables within the register stack. P1 is going to hold the return addresses within the register stack. And in addition to which, P1 also can hold the PSW, the program status word within the register stack. The moment P1 is suspended and P2 is incoming, the program 2 is incoming, the register stack must be emptied because the register stack is only the property of the currently executing program. In this light, you need to understand that whichever the program that is being executed concurrently within the CPU is going to use the register stack. The moment it is relocated back to the main memory, it has its own and specific stack. Independent individual stack, whatever you call. The stack will be utilized by that specific program. Now, this is the difference between register stack and memory stack. Now, let us talk about the design operation of the register stack and memory stack. Now, initially, we will talk about the design of the register stack. Before I talk about the design of the register stack, let us understand about the people who is going to support the stack. There are a few people coming to the picture whenever we talk about a stack. The first one is something called stack pointer. Second one is something called data register. Third one is something called a flag which is called full. Fourth one is something called a flag which is called empty. Fifth one is an operation that is going to be performed on a stack, that is push. And the sixth one is another operation which is called pop. Let us understand about these guys. Stack pointer is a register which is going to hold the address of the top of the stack. Data register is a register which is the origin and the destination for the elements of the stack. We're going to discuss about the data register in detail in a short while. Full is a 1-bit register which is going to show the status of a stack. If the stack is full, full will be equal to 1. If the stack is not full, full will be equal to 0. So before you perform any push operation, you are going to check with the full flag. If full flag is already 1, you are not going to push any more elements into the stack. Similarly, empty. If empty is equal to 1, stack is already empty. You cannot pop any more elements. If you want to perform a pop operation, first you ensure that empty is not equal to 1. If empty is equal to 1, implies 2. The stack is already empty, so the pop operation cannot be successful. Push is an operation which is going to add the items to the stack. Pop is an operation which is going to retrieve the elements from the stack. Now let us understand how the stack is going to be designed. Let us say I'm designing an 8-element stack. Now initially, stack pointer points 000, which is considered to be the base of the stack. Whenever stack is empty, the stack pointer is going to hold the address of the base address of the stack. That is 000. Now the stack pointer holds 000. The size of the stack pointer is 3 bits because the stack size is 8 elements. Now let us say you want to perform a push operation. When the push operation is performed, initially stack pointer will get incremented. That is, SP is equal to SP plus 1. Now the stack pointer moves from 000 to 001 as it is incremented. Now, after incrementing, the element will be pushed into the memory of the stack pointer. That is, contents of the data register will be pushed into the memory of the stack pointer. Now you can understand why we do require a data register. Every time when you want to push an item into the stack, the contents are taken from data register. Again, every time when you want to pop an item out of the stack, the popped element will get transferred to the data register. So hence you can understand the data register is source as well as the destination for an element to be pushed or to be retrieved. Now, initially stack pointer has been pushed, after which stack pointer becomes 001 from 000, after which we are going to push an element, data register contents will be moved. So let us say element 1, I will say A1 has been pushed. Now, one more element has to be pushed. Again, stack pointer will get incremented, element 2 will get pushed. If you want to push one more element, stack pointer will be incremented again, element 3 will get pushed. Stack pointer will get incremented again, element 4 will get pushed. Stack pointer will get incremented again, element 5 will get pushed. Stack pointer will get incremented again, element 6 will get pushed. Stack pointer will get incremented again, element 7 will get pushed. Now let us understand, still this 000 is free. Is there any way that I can use this 000th location? Initially you can understand, when the stack is empty, stack pointer is showing the base address, that is 000. And the first element is going to be pushed in 001, because you know that every time when you perform a push operation, stack pointer should be initially incremented, after which the element will get pushed. Now in this case, when we reach the top of the stack, that is 111, in this case, the final element, which is A7, considered to be pushed. But after which, are we going to stop Or still, is there any way that we can use this element? Here at this point of period, you have a doubt that why this is empty. Is there any way that we can use this? Of course, we will be able to use this location also. How? You know that initially when you perform a push operation, stack pointer is getting incremented. What is the size of the stack pointer? Size of the stack pointer is just 3 digits, right? Now, the moment stack pointer reaches 111, stack pointer value will be equal to 111, right? Now, you want to perform one more push operation. What is going to happen? 111 will be added with 1. What is the value of 111 plus 1? 111 plus 1 is equal to 1,000. Here in this case, only the least significant 3 bits will be accommodated into the stack pointer and the most significant digit will get discarded, since the stack pointer is just a 3-bit register, because the size of the stack is 8 elements. So the stack pointer size is fixed. It's always 3 digits. So the moment it reaches 111 and you want to perform one more push operation, of course it is absolutely possible, because 111 plus 1 is equal to 000, since the end carry will be obviously get discarded. So from A7, which is available at 111, if you want to perform one more push operation, 111 will get incremented, after which you will be brought back to 000. So finally, element 8 will get pushed in 000. So now you can understand that the initial top of the stack and final top of the stack will always be 000. Now, understand what it is. What is initial top of the stack? You know that stack pointer always holds the topmost element of the stack. When the stack is empty, stack pointer is showing 000. When the stack is full, still the stack pointer is showing 000. This is simply because the moment 111 is reached and one more increment is performed on the stack pointer, the stack pointer will be reset back to 000. In which 000, the final element will get pushed. So no element of the stack will obviously get wasted. This is how the stack is going to be designed within the CPU. The CPU stack is essentially used by the program which is being executed concurrently. When this program is suspended and one more program is incoming, the current stack will be freed and it will be allotted to the incoming program. The outgoing program is going to collect all the values from the stack and it is going to dump those values in the memory stack which is allotted to her, as I told you just a short while ago. This is how register stack has been designed. Okay, now let us understand about push and pop operations. When the push operation is performed, initially the stack pointer gets incremented, after which the contents of the data register will get transferred to memory of stack pointer, and we are going to check if the stack is already full. If SP is equal to 0, then full will be equal to 1 and empty is equal to 0. What is SP is equal to 0? Let us understand. When stack is full, what is the value of the stack pointer? Stack pointer value is equal to 000. Yes or no? Stack cannot be full if the SP is equal to 111. If the SP is equal to 000, then it is considered to be full. Now, whenever SP is equal to 0, then full is equal to 1. Understand this very carefully. After a push operation, if you reach to 000, that is the starting address of the stack, that means that the stack is full. After the pop operation, if you reach to 000, that means that stack is empty. Now you can understand. SP is equal to SP plus 1. Let us say SP is equal to 111. That is at the 7th element. Now 111 plus 1 is equal to 000, because 1 is discarded. So we will be brought back to 000. At 000, what element will get pushed? The element which is available in the data register will get pushed. Now we will check what is stack pointer value. If the stack pointer value is 0, then we reach the end of the stack. That is, full will be equal to 1. There cannot be any more element pushed into this stack. So when full is equal to 1, empty cannot be equal to 1. Either full can be equal to 1 or empty can be equal to 1, but not both. This is the difference. So when the pop operation is going to be performed, initially pop operation is just the retrieval of memory of the stack pointer into the data register, after which SP will get decremented. And then we are going to check with another condition, that is, if SP is equal to 0, then empty is equal to 1, full is equal to 0. Once again, let us have a quick recap of what happened in the stack. Initially, stack pointer is equal to 000. Now, let us say that the stack is completely empty. 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now, initially stack pointer is equal to 000. Now I want to perform a push operation. During a push operation, what is going to be done? Stack pointer will get incremented. So element 1 will get pushed. Again, I want to perform one more push operation. Element 2 will get pushed. Element 3 will get pushed. Element 4 will get pushed. Element 5 will get pushed. Element 6 will get pushed. Element 7 will get pushed. Now, 111 plus 1, 1000. Stack pointer is of just 3-digit register. So, will be brought back to 000. Stack pointer holds 000. Now, element 8 will get pushed. Now, every time when you perform a push operation, we are going to check with the stack pointer. If SP is equal to 0, then full is equal to 1. Obviously, this SP will be equal to 0 in two conditions. When the stack is empty or stack is full. After performing a push operation, if we come to 000, that means that the stack is full. Now, let us say I want to perform pop operations right now. Pop operation initially retrieves an element, after which stack pointer gets updated. That is, the topmost element will get transferred to the data register, after which SP gets decremented. Now I need to check if SP value is equal to 000. Let us say stack is completely full. Element 8 is available at 000. Now what will happen when we perform a pop operation? From 000th location, element 8 will get transferred to the data register. Then stack pointer will get decremented. SP is equal to SP minus 1. So 000 minus 1 is equal to 111. There is a phantom borrow method applied. So 111 will be reached. Now we are going to check if SP is equal to 0. After performing a pop operation, we are going to check if SP equal to 0. If SP equal to 0 after a pop operation, that means that stack is empty. We are going to set the empty flag to 1 and full flag to 0. Now, here in this case, 000 minus 1 is equal to 111. SP is at 111 right now. As SP is not equal to 0, this if condition fails. I want to perform one more pop operation. That is, from memory of the stack pointer, the contents will get transferred to the data register. That is that from the memory of 111, 7th element will get transferred to the data register. After which SP will get decremented. That is, SP is equal to 110. Right? Now again the condition will get checked. If SP is equal to 0, now the condition fails because SP is equal to 110. Finally, after the final pop operation, that is, the element at the 001 is retrieved, the stack pointer will be decremented to 000. At that time, this condition gets satisfied. The SP will be equal to 0. At that time, empty will be set to 1 and full will be equal to 0. So, push operation has these following sub-operations. Pop operation has these following sub-operation. The only difference between push and pop is, in the push operation, initially we are going to update the stack pointer, then add the element. In the pop operation, first you retrieve the element, then you update the stack pointer. So after a pop operation, if the stack pointer is equal to 0, then the stack is empty. After a push operation, if the stack pointer is equal to 0, then the stack is full. This is the difference between push and pop. Okay. Similarly, the stack can also be implemented in the memory, which is called a memory stack. Here you can clearly see, this is the memory. This is the memory. In the memory, there are multiple stacks. Each and every program should be supported with an exclusive stack, which is owned by the program. Let us say there are 100 programs. All these 100 programs must be provided with 100 different stacks. Each program is going to use its own unique stack. Now, how to design a memory stack, which is simple, as simple as designing a register stack. All the things that we discussed in the register stack will also be applicable to memory stack with one small difference. What is that? In the memory, the stack is not completely bound. What is it exactly? What we are talking about? What is this bound? Let us understand. When it comes to the main memory, let us understand that the main memory size is, let us say, 0 to 100. Now, I want to design a 8-element stack from 100 to, let us say, 93. This is an 8-element stack. Let us say this is an 8-element stack. Now, the difference between register stack and memory stack is the register stack is simply 8 locations, and these 8 locations are not part of any memory location. These are exclusive locations for stack. But when it comes to the memory, we need to obtain only a few memory locations, after which rest of the portion will be the property of main memory. It cannot be used for stack. Now here, let us say, the moment the top of stack is reached, it is not taken for granted that you are going to reach back to 100. Here, no matter wherever you go, finally you will come back here because of the stack pointer provision. The stack pointer is just 3 digits. So the moment you reach to 111, 111 plus 1 will get you back to 000. Obviously, you will always be in the vicinity of the stack. You cannot go anywhere else. But when it comes to the memory, the things are different. Okay, here let us understand. There is a slight difference. Here the stack is starting from the maximum address, ending with a minimum address. Now, you can understand, during a push operation, stack pointer will get decremented. SP is equal to SP minus 1. During a pop operation, stack pointer will get incremented. SP is equal to SP plus 1. This is the only difference. Within the register stack, SP can be equal to SP plus 1 because it is in the linear order from 000 to 111 in the ascending order. The addresses will get accumulated in the upward direction. But here, the addresses are getting updated in the downward direction. Initial address is 100, the final address is 93. In this case, you can clearly understand the stack pointer will get decremented during the push operation, incremented during the pop operation. Now, this is something new for you guys. For you guys, always the thumb rule is push operation is associated with incrementing the stack pointer, pop operation associated with decrementing the stack pointer, but actual design semantics are different. A designer will always choose a downward stack. Downward stack meaning push operation will be associated with decrementing the stack pointer. Pop operation is associated with incrementing the stack pointer. Okay, now another question is, the moment you reach 93, you cannot go to 94. One more subtraction, one more decrementing the stack pointer value will take you to 92. It is not 94, 92. 92 is out of the boundary, right? So 92 cannot be accessed. So what we do is, we will use registers in which stack boundaries are specifically mentioned. I will use 2 registers. In register 1, I will use one boundary. In register 2, I will use another boundary. Obviously, boundary 1 will be memory of 0. Boundary 2 in our case is 92. When these boundaries are identified, again the stack pointer will be set back to the vicinity, in the very vicinity of the stack. Let us discuss about this clearly. I'll explain you with a good example. This is the 100th element. As 100 is not possible, I can say this is 64th element. Total main memory size is 64. This is 0th element. So the memory will be addressed by using 6 digits, right? Stack pointer size should also be equal to 6 digits because one memory address is equal to 6 digits. Now 64 is 111111. The initial address is 0000000. We are talking about memory addresses. Now initially the stack is empty. So stack pointer shows 64. Okay. Then a push operation is performed, meaning stack pointer gets decremented initially, that is 63, in which the element 1 will get pushed. Okay, the final element is 64, 63, 62, 61, 60, 59, 58, 57. So the final element will be at 57 as an 8 element stack. 57. So let us say element 7 will get pushed. One more push operation requires the stack pointer should be decremented further, that is 56. Okay, so here one boundary of the stack pointer is 56. 56 is out of the stack. One more boundary is 0th location. So initially one boundary is reached. Every time when you perform a push operation, you need to check with this boundary. If the stack pointer is equal to 56, meaning stack pointer during the decrement operation, it went crossing the boundary. Now you need to set the stack pointer back to the desired one. SP is equal to 64. After 57, you will come back to 64, but not to 56. But the convention of decrementing the stack pointer will take you to the 56, in which you're going to check if SP is equal to 56, then you're going to make stack pointer manually to 64. So stack pointer will come back to the 64 with this instruction, in which you're going to put the final value. Similarly, 64 is 111. Let us say the final element A8 has been stored. Now I want to perform a pop operation. During the pop operation, what is going to be performed? Stack pointer will get incremented. SP is equal to SP plus 1. Now you can clearly understand SP is equal to 64. 64 plus 1 is equal to 0. That is the 0th location. Why 64 plus 1 is equal to 0? 64 is 111. 111 plus 1 is equal to 1, 000, 000. 1 will get discarded because a memory address is just of 6 digits. So we will be going again out of the stack. When you pop the final element, your intention is to come back to this element. But accidentally, what is the resultant address? The resultant address is the 0th address. Because the pop is involved in an addition, SP is equal to SP plus 1, during which 64 plus 1 becomes 0th address. So at that time, if SP is equal to 0, then SP is equal to 57. So manually, you need to correct this. Let us watch this video as many times as possible, since it is going to give you an exposure to the complete memory stack. So far, you are in an illusion that stack pointer will always get incremented during a push operation, always decremented during a pop operation, which is in contrast, going in a different way. Being a designer, you should understand push operation decrement the stack pointer, pop operation increment the stack pointer. When it comes to the memory stack, stack boundaries must be precisely set. All those boundaries must be obtained to the registers. Every time when you perform the push operation or pop operation, these boundaries must be checked, because you are not allowed to go out of the stack. So boundary should always be checked with. If the boundary value has been reached, then you need to set the stack pointer back to the actual location to which it has to get located actually. So this is the difference between a register stack and a memory stack. Thank you.